Everyone, this is Mrs. Whitaker. Today we are going to be talking about series circuits, and we want to be able to use mathematical thinking to examine the current, resistance, and voltage of a series circuit. We have talked about series circuits before, and if you remember, a series circuit is just a circuit with one path for the current. So here's an example of a series circuit. We have a battery with only one cell, we can call it just one dry cell, and then it's going to come over here. The current goes this way, and it comes to 3 resistors, and the resistance of a circuit is the sum of all the resistors. For a series circuit, that means it's going to be the equivalent resistance is equal to R1 plus R2 plus R3 in a series circuit. So we have an example here where we have our battery, and if we want to know the total resistance, the equivalent resistance, you can think of it as the total resistance, is equal to 4 ohms. So R1 is 4, R2 is 1, and R3 is 3 ohms. And we can just add them up. 4 ohms plus 1 ohm plus 3 ohms is equal to 8 ohms. Now, the current is the same at all points in a series circuit. I is equal to I1 equals I2 equals I3. So the current is the same no matter where you're at in a series circuit. So here you have the potential difference. This is what we're also looking at. The potential difference across the entire circuit is equal to the sum of the potential differences. All the voltage gets used up. As the current journeys along the circuit, each element will use some of that potential difference until it's all used up. So the total is equal to the voltage 1 plus voltage 2 plus voltage 3. And this leads us to Kirchhoff's second law, the loop law. It just says that the net electromotive force around a closed circuit loop is equal to the sum of the potential drops around the loop. That's just saying that V total is equal to V1 plus V2 plus V3 for a loop, which is a series circuit. Oops. We'll talk more about this in parallel, and you'll see how this can be applied differently. So here's a practice problem. We have the voltage as for the total is 100 volts, and we want to know what the values for A2, the current 2, the current 3, the voltage 1, and the voltage 3 for right now. So when we do this, we are going to use V equals I R, or R equals V over I, which is in your reference table. And what we're going to do is we can say that for V1, which is here, it's going to be the current, which is 2 amps. Remember, current doesn't change. So it's going to be I times R1, which is equal to 2 amps times 20 ohms, which is 40 ohms. And then V3 here is I times R3, and that's going to be 2 amps times 2 ohms, which is 4, oops, this is not the times amps, which is a volt. So this is 4 volts. So then we want to look at the current. The current is going to be 2 amps and 2 amps because current doesn't change in a series circuit. Okay, so here's the answer a little neater. Then we can go and solve for this R2 that is also here. And when we solve for R2, what we have to realize is that we can, we first have to find the total resistance. We need to find R equivalent. What is that for the whole circuit? So R equivalent is equal to the V total over the current, and the V total is that 100 volts over current, which is 2 amps. So the R equivalent is equal to 50 ohms, but we already have 20 and 2. So if you remember the equation, it's the R equivalent is equal to R1 plus R2 plus R3 for this one. So it's going to be R equivalent is equal to 20 ohms plus R2 plus 2 ohms. So it's then 22 plus R2 is equal to 50 ohms. This goes here. So then it's 50 minus 22. So then it's going to be 28 ohms is equal to R2. So R2 is equal to 28 ohms. The current is still equal to 2 amps. Voltage is going to be IR. So it's going to be 2 times 28, which is equal to 56 volts. All right. Thank you.